Okay, this is going to be an overview of the activity I'd like you to complete today, in which you're going to be learning a little bit about how natural selection actually affects populations in the real world, using an example of cacti and peccaries, which are a predator of cacti in the wild. So what I'd like you to do is, on the case study that you have taped into your notebook, I'd like you to go ahead and read that first paragraph, and then pause this video after you've read the first two paragraphs, and I'll explain what they were saying. Okay, so the first setup for this scenario basically talks about prickly pear cacti. Here's a couple of pictures of prickly pear cacti with different numbers of spines, and you see a graph on your sheet that shows the number of spines on prickly pear cacti, and basically this is an example of variation. The first few questions on that page ask you to analyze variation. I do want you to watch carefully this graph, or look carefully at this graph, because in the next couple of scenarios you're going to be expected to predict how this graph is going to change. And on this graph we see the number of spines. So on the left there are fewer numbers of spines, on the right there's more spines, and then we also see the number of cacti that have those spines. Some students are curious why cacti don't just all, tend towards varieties that produce the greatest number of spines. Now you got to remember, producing spines requires energy for the plant, so it's not going to produce spines or grow spines unless there's some advantage to doing that. So there must, in this population, this normal population of cacti, be a best advantage somewhere around 90 spines, where we get the most cacti with that in the population with the genes that produce 90 spines. Fewer than that must be at a disadvantage, and more than that probably uses too much energy, wastes too much energy making spines, and doesn't have enough left over for reproduction. So go ahead and answer those questions. I'm going to pause the video. You should as well. And then I'll review the answers to those first couple of questions. Okay. Hopefully you paused the video and answered the questions. If you didn't pause the video and answer the questions, go ahead and answer them now, because you really need to have thought about these questions before I go over them. These questions look much like the kinds of questions you'll be asked to do on the assessment. That's not very in focus. Let me focus that a little bit. So answering these effectively is going to prepare you for the assessment that you will take on Monday. So the first part is just an overview question. What is the evolution equation? And for that, you guys should have answered that the evolution equation is genetic variation plus selection plus time. The differences in the number of spines is which part of the equation? This is variation. Okay. So, the description above says that there have not been predators for a long time, so there's been little struggle for existence, and as a result there's been no change in this population over time. Explain why there's no change in the population over time using the evolution equation. The answer to this is, if there's no struggle for existence, remember that's part of natural selection, then that means there's going to be no selection. So natural selection will not be picking the better varieties because they all do equally well. There's no advantage or disadvantage. So no natural selection means no change in certain genetic varieties. Hence, no evolution. Okay. Then the next one, why do cacti have different numbers of spines? This is what we covered on Monday, where you need to use the concepts of DNA the sequence of DNA, proteins, and how they're created and how they lead to traits. This is absolutely going to be on Monday's test. You should try this and be ready to show me your answers tomorrow. According to the graph, which of the above variations is the most common? Now I want to go through this one because I want you guys to see what this graph shows. This shows number of spines and number of cacti with those spines. Obviously this is the highest point. So this means that 90 spines is the most common variety. That means in this population, genes that produce 90 spines per plant or per pad is the most common. Okay? So let's go back here. So we're looking at somewhere around 90. We're not looking at a very spiny cactus like this, and we're not looking at a very, naked cactus like this one. So then we're going to go on and we're going to look at some scenarios. So please turn the page over. You do need to make a couple of changes here at the top. I don't know what I was thinking when I wrote this out, but basically delete that and add the word food at the end of the sentence here. You can also delete this. It'll make that sentence more understandable. So they're going to add peccaries, which are a predator to the cacti, to this case study, and then think about what is going to happen to the population of cacti. So let me show you some pictures of that. Here's what we're really thinking about. Peccaries. This is a peccary. Wild pig. They're also called javelinas. They live all over the Southwest, and one of their main food sources, believe it or not, is prickly pear cactus pads, and they'll eat them despite all of those big spines. So here's a chunk out of one of those prickly pear cactus pads that that a peccary has removed. So they just chomped that right off. So in that example, they talk about how peccaries, for obvious reasons, prefer to eat prickly pear cacti that have fewer spines. It's more comfortable for them, even though their mouths are tough enough to deal with them. If they have a choice between a very prickly one and one that doesn't have so many, they will choose the pads with fewer spines on them. So as you think about this population of cacti, which cacti are more likely to reproduce, and how is that going to affect that graph that we saw here? Okay, if they select these individuals and eat them first before eating these, which genes are going to start to become more common, and what will happen to the graph? I'm going to pause that there, answer the next two questions, and then once you've answered them, start the video again and I'll show you the answer. Okay, so I hope you've answered those questions. If you haven't, stop the video and answer them before you look at this. So this is how we would expect the graph to change. If the peccaries eat the cacti with the fewer spines on them, these individuals are going to get selected against. Those cacti with more spines are going to be selected for, and over time, natural selection will push evolution in one direction. So the population, the varieties that will become more common will be those that have more spines in them. This is called directional selection because there's a direction to what natural selection is doing. Okay? Alright, so now try the next scenario where a wasp is added and see if you can decide what's going to happen to the population as a result of adding a wasp. And I'll pause it, and you should as well. Okay, so here's a graph of what we would expect would happen to the population in this next situation where we have peccaries pushing the population, eating those with fewer spines, and we have parasites eating or destroying those cacti that have more spines. So they're pushing from both sides. This is called stabilizing natural selection because it tends to concentrate the varieties in one area. This is actually the most common kind of natural selection in our world, where there's forces from one side pushing the population one way, forces from another side pushing varieties in another way, so you get most individuals in the middle. So they have this trait becomes the most common, and there are almost none on the either extreme. And this is why when we think of most plants and animals, we think of them as all looking the same. And that's because natural selection is pushing from both directions. It doesn't mean there aren't other varieties. It's just that varieties in any other direction other than the main or the central area, in this case 90 spines, are selected against. So this is called stabilizing, where everything gets pushed into the middle and stabilizes the selective pressures so that there's one trait that becomes the most common, as opposed to directional selection that pushed traits in a certain direction. Pause it again, and now read about what happens when the wasps are removed and the peccaries are removed, and all we have left are people. So pause it, and we will get back to that in a second. Alright, so here's the final scenario, and in this case we've got tourists. Ignore for a second these goofy pictures at the top of this scene here. I don't know, something out of the 1950s, all very, I don't know, wholesome looking. Although these people do not look like at all like they're in a desert, but whatever. Let's pretend that we've got tourists. They tend to like to pick cacti that have about 90 spines because those are the best looking cacti. They dig them up, they take them out of there, which means they've selected them. In that case, 90 spine cacti are going to start to become less common. Okay, and in this type of natural selection, we see a selective pressure down on the center population, and we end up with 2 spikes on either side. Okay, because these become less common, the ones to the left and the right are going to become increasingly common. So this is the third kind of natural selection. And now I'd like you to read a little scenario about squirrels in my backyard, and if you remind me tomorrow, I'll get out my albino squirrel and I'll show you the last of the albino squirrels from that case study, or where that case study came from, and tell you a story about my dog. So remind me about that tomorrow. Make sure you've got good quality answers on this, and yeah, I'll see you in class on Thursday. Thanks. Bye.